Hello and welcome to video number 5 of the A1 series. Today we're going to be looking at the derivation of the 5 Suvat equations, and then we're going to be using them to solve for motion in one dimension. Then we're going to be looking at setting the positive direction and looking at 2 of my own worked examples. And then we're going to look at practice questions 14 and practice question 15. Please enjoy the video. Hello and welcome. This is video 5 in the A1 series, and today we are going to look at the derivation of the 5 equations of motion. Forget the book and its 4 equations, there are 5. So we start with a velocity time graph. No numbers. We have a situation where something starts at velocity u, u standing for initial velocity, and changes speed at a constant rate, so changes its velocity at a constant acceleration, and ends up doing velocity v. So it's going from u and increasing to v at a constant rate because the line is straight. And it takes a total of t seconds to do this. Do you agree that the change in speed can be thought of as the final speed can be thought of as u plus the change in speed. And the change in speed is the acceleration, which is the change in speed per second, times the time. So acceleration times time, at, is that bit. So we have v, final velocity, equals u, initial velocity, plus change in speed. Now in the book, I'm not going to have an argument over this, in the book that's called the first equation of motion. I'm happy with that. Let's call that number 1. Okay, so now we're going to look at the second and third equations of motion, and they involve displacement s. This again is the same graph I just showed you, velocity against time. And if I said to you, how far have we travelled between time 0 and time t, you would say, oh, I know how to do that. It's this distance, it's this nice rectangle there, plus this triangle. Well, what's the area of this bottom rectangle? Well, that's just u times t. And what's the area of that? Well, this side is the change in speed, which can also be written as acceleration times time, and this is time. So this entire box here, this top bit of box here, the area of that rectangle is a times t times t. A times t is that bit, and t is that bit, so the whole box is at squared. But we don't want the whole box, we just want this half, so it's half at squared. And so equation number 2, displacement s equals ut plus a half at squared. Now there's another way of doing this. If you look again, another way of working out that area is to add together this rectangular box, which is ut, but instead of adding that triangle, why don't you work out the whole thing and take away that bit to get that bit? So what about motion equation number 3, which is not in the book, which I'm going to give you as a special? Another way of looking at this whole graph is to say that the distance covered, which is this bottom rectangle and that triangle, is the same, I need to get another colour here, is the same as this entire box, which is v times t. So if you take the whole red box and you take that away, you'll get all of that, won't you? So it's v times t, take away half at squared, and that is what I call equation of motion number 3. And I think it's important because this one doesn't contain u, it contains v in its place. That's not in the book, but it used to be one of the 5 that we used to teach. Okay, so my 4th equation is a real simple one. In words, its displacement is equal to, in words, average velocity times time. So here we've got u and v. Here we've got a velocity time graph. The speed is increasing to time t. One way of working out the area under the graph, instead of adding that rectangle to that triangle like we did for 2 and 3, why don't we think about squishing this down into a rectangle? Do you agree that if I just drew a halfway mark between u and v there, yeah, across there, the area of this rectangle will be the same as the area under that line? Because I've just found the halfway mark, and I've got the average. The average velocity will be the average. How do you work out an average, everybody? You add things together and divide by 2, don't you? You go v plus u and divide by 2, and that gives you the average velocity, and then you multiply that by time. And that is number 4. V plus u over 2 times t equals s, displacement. Okay, so just to recap the first 4. Number 1, final velocity is initial velocity plus acceleration times time, which is change in velocity. Number 2 is your displacement is your initial velocity times time plus half acceleration times t squared, and that corresponds to the triangle in the graph I showed you. Another way of looking at it, instead of using u, we can actually say that s is vt, take away that little triangle. So that's 1, 2, 3. Number 4 is straightforward. Displacement is average velocity times time. Easy peasy. Now number 5, the last one, is much trickier and is simply derived. And what we do is we basically take number 1 and we turn it around and we say that the change in velocity, v minus u, divided by a will give you time, which makes sense. If I have 2 velocities, 8 and 12, started at 8, accelerates up to 12. The change is 4 meters per second. And let's say it took 2 seconds, the acceleration is 2 meters per second. 4 divided by 2 tells you that it took 2 seconds to change. So we're going to use this formula, v minus u over a equals t, and what we're going to do is we're going to substitute that bit, v minus u over a, where t occurs in here. So all I've done is I've rewritten this here. That's t, and that's t squared. V minus u over a all squared. So that's your starting position. The next thing we're going to do is we're going to multiply everything by a. If I multiply this side by a, I multiply this side of a and it cancels off. I multiply this side by a, goes to there, and the second a cancels off there because I've got an a and an a squared on the bottom. And you end up with this position. As equals u times v minus u plus a half v minus u times v minus u. And expand that out. First things first, we'll get rid of the 2. We'll multiply both sides by 2 first. So we have 2as equals 2 times this, which is 2uv minus 2u squared, plus, the half's gone because I've multiplied it by 2, plus v minus v times v squared, minus 2 lots of uv, plus u squared, because minus u times minus u is plus u squared. Now look carefully, everybody. This is great. I love cancelling. I've got 2uv take away 2uv. So that cancels out. I've got a plus v squared, nothing to cancel against it. But look carefully here. I've got a plus u squared take away minus 2u squared. So it simplifies down to v squared minus u squared. And this is what I call the 5th equation. 2 times acceleration times displacement is equal to the difference between the velocities squared. Now, because velocity is a vector quantity and will be plus or minus, because we're squaring it, we're just squaring the magnitude. So this is number 5. I'll put it up here. Number 5, 2as equals v squared minus u squared. Now, here's the interesting thing. If you look at all of these, you'll notice that they all have 4 of the 5 Suvati things in them, and they're all missing 1. Let's write down for each one which one is missing. Do you agree that this one is missing S? This one is missing V. This one is missing U. This one is missing A. And probably the most important one, this is the only one that misses out on T. Now, if we swap round, interestingly, if we make S equals VT minus half AT squared, number 2, and swap that with swap 2 and 3 around, you would actually have it spelling out Suvat, which is quite cool. But here's what you need to know. You are given these equations, they are on your data booklet, you don't need to learn them by heart. What you need to know is how to use them to solve something. We're going to do one worked example with me. It's the first one. Somebody is standing at the top of a 30-metre high cliff. They throw vertically up an object at 8 meters per second. It goes up and round and down, and what we have to do is we have to work out what V is when it hits the beach 30 meters below. So let's go through how you work this out the official logical way. You write the letters S-U-V-A-T. Let's do that. And we write down what we know. Before we start, I mentioned this earlier, but it's really important. From now on, for all projectile questions, I am going to have up as the positive direction for displacement, the positive direction for velocity, and the positive direction for acceleration. There are 3 different things that have a positive direction, okay? And they're all got the same positive direction. And I'm choosing up. All right? So, the first thing, displacement. From here to where it finishes is 30 meters. But because I have defined up as positive, that displacement is minus 30. U, initial velocity. 8 meters per second upwards plus 8. V, wanted. Acceleration. Oh, I haven't mentioned acceleration. Well, the acceleration is the acceleration due to gravity of a projectile. And now what we're going to do here, to keep it simple, in your thing, I think you're supposed to use 9.81, but I'll get back to you on that when I've done some research, depending on what it teaches. I'm going to use 10 meters per second for these calculations because it just makes life so much easier, okay? So think about the acceleration. The acceleration is downwards, so it's minus 10 meters per second. And time, we don't know. I've now got 3 things, S, U, and A. And I am missing V and T, and I want V. The one I don't need is T. So I now look at my 5 equations. Which one of my 5 equations lacks the thing I don't want, which is T? Number 5. So I am going to use number 5 to solve this. 2as equals v squared minus u squared. That's how I think of it. It's also v squared equals u squared plus 2as, but I prefer it that way around. All right. And I want to find v, so in fact I'm going to put v on one side. So v squared equals, if you think about this, if I add u squared to both sides, u squared plus 2as. Are we cool? U is 8. U squared is 64. 2 times minus 10 times minus 30. Minus 300 times 2, 600. One more time. 2 times minus 10 times minus 30. That's 300, 600. Now, look at the sign. I've got a minus times a minus, that becomes a positive. So this is plus 600. Get my calculator out. 64 plus 600 is 664 is v squared. Square root it. 25.77. I'm going to work to 2 decimal points in all my projectile questions. 25.77. 25.77 meters per second going down. Great. Solved. But what would have happened if the person, instead of throwing it up at 8, had thrown it down at 8? Well, because it's getting squared there, there's absolutely no change to this v. Can you see that? Because that would still be 64, and that would be the same, and you'd end up with the same answer of 25.77. Now, as a physics teacher, I find that deeply unsatisfying because I can't see that answer is right. It sounds about right, but I can't see it that it's right. What do I need to do? Well, I need to work out, for example, how long it takes. If I know how long it takes, I'll be a lot happier. So why don't we look for time here? I need to start putting up some red flags here because many of you will be told or taught to start to use that thing to extract t using a quadratic. And when we do some more worked examples, we'll briefly look at that. I'm trying to avoid using a quadratic equation to find t because I don't think you should be using quadratic equations in physics examinations. All right, there's other ways to do it, and the other way to do it is to work out v first. So now let's look at what we've got here. We've got it starting at plus 8 and finishing. Now here's the interesting thing. I'm saying it's 25.77 down. Its actual speed is minus 25.77. Its actual velocity is minus 25.77 because it's moving down. All right, you don't know that because obviously the square root of 664 could be plus or minus 25.77. You know it's going down. So it started at plus 8 and it finished at minus 25.77. What was the change in velocity? Well, 25.77 plus 8. The change in velocity was 33.77 meters per second. From the moment it left the person's hand to the moment it hit down there, it was accelerating at minus 10 meters per second. So that means its entire journey must have been 3.377 seconds. 3.377 seconds. Does that sound about right? Well, I want to just use the same example to just do a few more calculations with you. I want to just keep those numbers in mind, and I want to just teach something very, very basic. Okay, so what I want to do is I use the same situation to just talk a bit more about going into a bit more detail about the calculations. Do you agree that if I throw something up in the air at 8 meters per second and acceleration is minus 10, it will take 8 divided by minus 10, doesn't really matter about the sign there, it will take 0.8 of a second to get to the top. And it will take another 0.8 of a second to come back down again. Why? Because acceleration of minus 10 means that it slows down by 10, or in this case minus 10. It's slowing down by 10 meters per second every second. So in order to slow down by 8, it's going to be 8 over 10, 0.8 of a second. So I also know that it's going to get back to this point at time 1.6 seconds. And I also know that it'll be travelling down at 8 meters per second at that point. And we are 1.6 seconds into it. Okay, so we know it's going to take 0.8 of a second to go up, 0.8 of a second to come back. So after 1.6 seconds, it's back there and it's travelling downwards at 8 meters per second. How long is it going to take to speed up from 8 meters per second to its final velocity at the bottom, which we worked out at 25.77? How long is it going to take? Well, 25.77 take away 8, and divide, which is 17.7, and divide by 10, 1.78. 1.78 seconds. Now look, 1.6 and 1.78, what do we get? Total flight time of 3.377 seconds. Can we double check this number from these numbers? Yes, we can. If we use this time, we know that S equals UT plus half AT, UT plus half AT squared. Let's double check this figure. I know what U is. In fact, we don't even need to start here. We can start from that position with U being going down at 8. So S equals minus 8 times T. So T here is the time to go from there to there, which is 1.78. 1.78 plus a half times minus 10 times 1.78 squared. And if we tap all of that into a calculator, fingers crossed, we should come back to 30 meters. UT minus 8 times 1.78 equals minus 14.24. So that bit's minus 14.24 plus a half times minus 10, which is minus 5. Minus 5 times 1.78 squared. Minus 15.842. That sounds about right, but have I got my signs mixed up somewhere? Yes, it's a plus minus 15.84. Minus 14 plus minus 15.84 is the same as minus 14.24 minus 15.84, surprise, surprise, 30 meters. Now, it's a pain in the neck because so many students make mistakes over signs. You've just got to be careful with the signs. But it should all check back, and I would encourage you all, even on a simple question like this, to double check it. Double check from your final speed and, for example, your time, you can get back to the same number. Everyone okay with that? Okay, so we're now going to do a second example. Now, when you do real questions, you'll probably realise that most of the time, the thing you're missing is time. And you're probably going to be going for this formula to solve things because you haven't got time. But in this question, I'm going to give you time, so you don't want to be using this equation. I'm trying to get you away from equation 5 into using the others. So, here's another question. Somebody is standing at the top of a cliff. They throw a rock directly upwards at 6 meters per second. 6.8 seconds later, that rock hits the ground at the bottom of the cliff. What is the height of the cliff? That's my question. So, let's do this. Let's do this the first way, doing it the formal way. You write down S-U-V-A-T. S is wanted. U, all together now, up is positive. U, plus 6 meters per second. V, we don't know, and we probably don't need it. Acceleration, minus 10, acting under gravity. Time, 6.8. We have 3. We should be able to solve this. Can we find an equation there which does not have V but has the others? Oh look, it's number 2. So we're going to use that one. So we're going to have S equals UT plus 6 times 6.8 plus a half times minus 10 times 6.8 squared. And all you got to do is put the numbers carefully into a calculator. Let's go! 6 times 6.8. I suggest you split it. That bit is 40.8. And that's a plus with a minus, so this is all going to be minus a half times 10, which is 5, times 6.8 squared. 231.2. 40.8 take away 231.2 is minus, because it's below you, 190.3 meters. Does that sound about reasonable? Well, let's do a quick check here. Let's just do this very, very quickly. Rough numbers. It's going to take 0.6 of a second to get to the top and 0.6 of a second to come back down. So that's 1.2 seconds to there. So I'm telling you that it's taking 5.6 seconds to fall that distance of 190.3 meters. So we could then look for a t in there and solve and then check back. But you know what? It does seem about right. There's an awful lot of work involved if you want to go back and double check things. Find t, especially in this situation. That's a lot of work. Okay, so before I start getting into more and more detail into projectile questions, which we haven't really started yet because projectile questions are usually in 2 dimensions, I want to keep things to 1 dimension and look at the practice questions on here. We're going to do PQ14. PQ14, there is a little cart and it's launched. When you see the word launched, that means somebody has pushed it and then stopped pushing it. So its initial speed is 3 meters per second up the slope. Gravity is acting on it with a constant acceleration of 1.8 meters per second directed down the ramp. So we can say that its acceleration is minus 1.8 meters per second. Well, the first question is the time the cart takes to return to the starting point. Well, could not be easier. All you do is you work out the time it takes to slow down from +3 to 0. And every second you're slowing down by that much. 3 divided by 1.8. Forget about the signs. 3 divided by 1.8. 1 2/3, 1.667. If it takes 1.667 seconds to go up the ramp, it will take the same amount of time to come back down the ramp, because in physics land all accelerations are constant. So if I times that by 2, the answer is 3 1/3 seconds. So it'll take 3 1/3 seconds to go up and come back down. Part B, the maximum distance from the starting point. We can use a formula or we can use common sense. Do you agree the time it took to go from here to the top was that much? And do you agree that its average speed in that time was 3 plus 0 divided by 2? So 0.5 meters per second average speed. And average speed times time is displacement. 1.5 times 1.6667, 2.5 meters. It goes up the ramp 2.5 meters and then stops. This is one of my favorite equations. Average speed times time equals displacement. Average speed times time, number 4 on my list. This is the one you should be using a lot. All right, so the average speed is 1.5. Starts at 3, finishes at 0. Average is 1.5 times the time you found. Excellent. Okay, welcome back. Practice question 15. An aircraft accelerates from standstill to 100 kilometers per hour in a time of 16 seconds. What is its acceleration in meters per second per second? Stage 1, to go from kilometers per hour to meters per second, you divide by 3.6. So it's doing 27.78 meters per second. And we go 27.78 meters per second divided by the 16 seconds it took to change. And so we are looking at an acceleration of I'm going to keep it accurate, 1.736 ms to the -2. We are then asked for part B. We are told to take off, the aircraft must achieve a speed of 250 kilometers per hour. Okay, 250 kilometers per hour. I really don't know why they're wasting our time with kilometers per hour, because I'm pretty sure they don't do that in the questions. But anyway, so 250 divided by 3.6. So we're looking at 69.44 meters per second needed for takeoff. So before I even look at the question, I can work out how long it's going to take, right? So if I'm accelerating at that rate and I want to achieve that speed, how long will it take? Divide that number, divide 1.736. It's going to take, exactly 40 seconds. So it's going to take 40 seconds of acceleration, assuming constant acceleration, and most aircraft do not accelerate constantly. They accelerate faster at the beginning, and then they sort of level off towards takeoff speed. It's never constant acceleration, but never mind, that'll do. Calculate the minimum length of the runway required for takeoff, giving the answer to the nearest 100 meters. Assume that the acceleration is constant during the entire takeoff. Easy peasy, lemon squeezy. What do we know about distance travelled? Do you agree that distance travelled is average speed times time? The time taken is 40 seconds. It started at 0, it finished at 69.44. What's its average speed? Average speed is 69.44 divided by 2, 34.72 average. So if we multiply 34.72 by 40, it'll tell you how far it's gone down the runway. The runway is 1388.8 metres to the nearest 100, 1,400 metres. It needs 1,400 metres to take off. So we're going to wrap up video number 5 there, and we're going to pick up next time with finishing off the practice questions 16, 17, 18, and then we're going to start on proper projectile motion, which is in 2 dimensions, not just up and down, but sideways as well. I'll see you next time. Thank you.